Good morning. So my charge, as I explained last time, is to give you some basic background in superstring theory that will help to prepare you for the subsequent lectures. And the material is also, I think, of interest in its own right. Now, yesterday I sort of sketched material that's in chapter 6 of our recent book, and I intended to cover material from chapters 7 and 8 as well, which would naturally require 2 more lectures, even at the equally rushed pace to what I did last time. However, since I only have this 1 lecture, not 2, what I will do is try to cover material from both chapters 7 and 8. So 7 has to do with the heterotic string. I lost a piece of paper. Oh, here it is. So chapter 7 has to do with heterotic string, and chapter 8 has to do with Mtheory and non-perturbative dualities. And so each of these could easily take several lectures, so I'm only going to give you some of the highlights from each of these chapters. And excuse me for being somewhat rushed. I'll try not to be too rushed. I rather omit topics than rush too much. And still, please feel free to interrupt, of course, with questions. So what is the heterotic string? So that's what we want to discuss now. And so historically what happened was the bosonic string was discovered first, and it has a critical dimension of 26, in which everything is consistent except the fact that there's a tachyon in the spectrum and that there are no fermions in the theory. But otherwise, it's mathematically nice and gives much of the mathematical framework for understanding string theory. And then what was developed next was the superstring, in work I did with Michael Green, building on previous developments over the previous decade or so. And it has a critical dimension of 10. Now, in the study of the superstring, at some point it was realized that the type 1 superstring had anomalies unless the gauge group was SO32. And Michael Green and I realized that from a low energy effective field theory viewpoint, that another alternative for the gauge group that would also be consistent with the cancellation of anomalies was E8 times E8. But we were in the peculiar position that the type 1 superstring that we had constructed realized this symmetry, but we didn't at that time, in 1984, have a string theory that realized this one. So very quickly, following these developments, a group here in Princeton, Gross, Harvey, Martinick, and Rome, realized that the way to understand this theory in particular was to combine features of the bosonic string and the superstring to make a new string theory, which they called the heterotic string. So in their paper, they say that the Greek word heterosis has to do with increased vigor due to crossbreeding. So that's what they did by combining these 2 string theories. And so the idea, very simply, was to use the structure of the superstring, the 10-dimensional superstring, to describe the right moving modes of this new heterotic string. So the heterotic string is going to be a string theory which just has closed strings, no open strings. And as in the other theories, when you look at the world sheet theory, there is a separation in the structure of the left moving modes and the right moving modes for the usual reasons, because basically you're just dealing with a wave equation or a Dirac equation for the world sheet fields, and that always splits into a left moving equation and a right moving equation. So one could discuss the left movers and right movers separately. So to describe the right moving modes of the bosonic string, one uses the mathematics of the superstring. And for that, one can use either the RNS formalism or the GS formalism, which are described in earlier chapters, and I don't want to review it here. Whatever you do, this sector gives you massless modes that form a super Maxwell multiplet. So the massless sector that you obtain by either approach, it gives you a vector and a Majorana-Weil spinner. So Majorana-Weil. And so in terms of physical degrees of freedom, this has 8 transverse polarizations. This also has 8 polarizations, the equality being required by supersymmetry. And so sometimes we would write using a Fock space notation, I, where I runs from 1 to 8, to represent the 8 physical polarizations of this field, and say some other symbol A, where A runs also from 1 to 8, to represent the physical polarizations of the Majorana field. So whatever formalism you use, that'll be the massless sector of the associated with the right movers. So really the whole story has to do with how you treat the left movers and how you can combine them with this structure. So remember, here we have 10 right-moving space-time fields, and then depending which formalism we use, we either have some world sheet spinners or some space-time spinners that accompany them. And that's this choice of whether you use this or this has to do with which formalism you're using. So now let's immediately turn to the left movers. And now the idea was to use the structure of the bosonic string, which in the first instance you would say just has 26 dimensional left-moving modes. And just taken on face value, that seems a little peculiar, because how do you combine that with this in a sensible way? So to get 10 ordinary dimensions, it's convenient to split this up and to consider, first of all, 10 of them. And these 10 will be paired with these 10. So here the mu goes from 0 to 9. So that's going to be our 10-dimensional space-time. And to get an ordinary space-time dimension, you have to be both left-moving and right-moving modes. If you don't have both, it's not an ordinary dimension. So this can't be the whole story, but this should be part of the all left-moving story that will accompany this. But then we need more degrees of freedom, because one of the crucial facts about the bosonic string theory is that the world sheet conformal field theory has central charge 26 for its consistency. And one way of achieving that, which is what one normally does in the bosonic string, is just to have 26 of these x's, because each x contributes 1 unit of central charge to the world sheet conformal field theory. So if you're going to separate off 10 of the dimensions and treat them this way, this means there's 16 units of central charge left over that somehow have to be realized. And there are 2 different ways of doing it, which turn out to be equivalent. So one is to just introduce 16 more bosonic coordinates, which are the 16 that are missing here. And so we could call them XLI, where I runs from 1 to 16. So these will each give 1 unit of central charge. So these will be just left-moving modes. And there are further restrictions for this to make sense, which we'll discuss, suitably restricted. What this restriction means is that these are not just 16 non-compact coordinates. That wouldn't make sense. They're required to parameterize a torus of some sort. And the structure of the torus is very restricted in a way we'll discuss. So this is one formalism, which is known as the bosonic formalism for describing the left movers. And the alternative is to introduce a different system that also has 16 units of central charge. And it's known that a world sheet fermion contributes equal to half. So the way to get, one way that one can get 16 units of central charge is to have 32 worldsheet fermion fields. So since each gives a half, that gives you 16 units of central charge. Combined with this 10 will give you the requisite 26. So these are two different ways of building up C equals 16 for the left-moving sector of the conformal field theory. So these are left-moving fermions. I may later drop the symbol L, but it's understood that these are left movers. So each of these, there turn out to be two different constructions that will be consistent, and each of them can be described either in this formalism or in this formalism. So it doesn't really matter a lot which I describe first. They're equally subtle. They just have different issues. So let me start with the fermionic formulation. And in the fermionic description, that means using the lambdas. That's what I mean by the fermionic description. So we have these 32 lambdas. And now, in both the left-moving and right-moving sector, if you use the usual formalism, you have Virasoro constraints or super Virasoro constraints. And then you have a mass shell condition, which is that L0 has some eigenvalue. Remember, that's the zero mode of the Virasoro conditions. And in fact, the statement that the ground state of the right movers is massless is a consequence of the fact that L0 is required to have eigenvalue 0 for physical states. So there's some the supersymmetry leads to some cancellation of normal ordering constants, which leaves 0. But in these discussions, one often gets an offset. So, for example, in the fermionic description for these left movers, so let me use a tilde to indicate it's left movers. The eigenvalue has to be 1. And what that means is that to describe the massless states that match up with these, one needs 1 unit of oscillator excitation. So how can we make 1 unit of oscillator excitation? Well, the oscillators that come from the modes of the XL mu are oscillators sometimes represented as alpha n mu. Maybe I should put a tilde because these are left movers. And so, for example, one could have the first oscillator acting on the Fock space ground state would give me 1 unit of excitation. That would describe a vector, a space-time vector. And to get the physical spectrum, one has to tensor the right movers with the left movers. So part of the spectrum, then, is obtained from tensoring this state with these states. And doing that gives you 64 bosons and 64 fermions, because these are 8 bosons times these 8 bosons gives you 64 bosons. And those 64 bosons are the space-time metric, an antisymmetric tensor, and a dilaton field. So that gives you 64 physical excitations that one has in the massless spectrum. And so it's a gravity theory, because as always, because gravity's in there. And then tensoring this with the spinners gives you some Majorana, gives you a Rorita-Schwinger field, a gauge field for local supersymmetry, and another spinner called a dilatina. This is a Majorana-Weil spinner, and since there's just one of them, this theory will have n equal 1 supersymmetry in the 10-dimensional sense, which means that there are 16 supercharges. So the minimal Majorana-Weil spinner in 10 dimensions has 16 real components. So one already sees at this stage that one expects in this way to get a theory with n equal 1 supersymmetry in 10 dimensions, which is half the amount of supersymmetry that one has in the case of the type 2 strings that we were discussing yesterday a little bit. So that's part of the spectrum that one gets by these excitations. But now we also have these lambdas there. And for the lambdas, these are world sheet spinners. And these have to be treated by analogous mathematical methods to the world sheet spinners that one has in the RNS formalism of the superstring. And the crucial issue with the world sheet spinners is whether you give them periodic or anti-periodic boundary conditions. So we're dealing with a closed string where there's a parameter sigma that goes from 0 to pi that parameterizes the string as you go around it. And so when you shift by pi, fields are going to be either periodic or anti-periodic and under that shift. And so there are two different sectors that one has to consider, the periodic sector and the anti-periodic sector. So the lambdas can be periodic or anti-periodic. Let me just write P or A. And those would be the analogs of what are called the Ramond and NS sector in the case of the psi mu field in the superstring. It's mathematically the same sort of thing. Now, when these things are in the periodic sector, the moding is integers, so n. So n goes from, so the Fourier modes of these things, when you decompose into Fourier modes, these are functions of sigma and tau, and when you solve the Dirac equation and just write out a Fourier expansion, you get modes, and these modes would be integer in the case of the periodic case. And then when you take the anti-periodic boundary conditions, then these modes would be half integer. So z plus a half. So, and then the choice of exactly which sector you use and what further restrictions you impose has to do with what's called a GSO projection. And it's crucial to choose the correct GSO projection condition to get a consistent physical spectrum. And I don't really have time to go to explain the logic of that. You'll just have to trust me on it. But it's analogous to things that were discussed in earlier chapters that you're supposed to have read. So in the A sector, for example, where these lambdas have half integer, what we need to describe the massless sector, what we need, because this L0 tilde is 1, which is actually true in the A sector. That's not a correct the value of this constant depends on which sector I'm talking about. So in the A sector, this constant is 1. And so to get states that will be massless, what we need to do is to have, since these lambdas have half integer indices, we have to use two of them acting on a Fock space ground state to build up one unit of excitation. Minus a half plus minus a half is minus 1. That gives me the 1 unit of excitation to get up to the massless level. Without any excitations, just the pure ground state would be a tachyon, just as it is in the case of the bosonic string. But in this case, the tachyon is automatically projected out of the theory because of the level matching condition, which says that the mass level that you get from the right mover has to mesh with the mass level you get from the left mover. And since there's no tachyon in the right mover sector, the left moving tachyon is automatically projected out of the theory. As it must be, since we're dealing with a theory with a gravitino, which tells us it's a locally supersymmetric theory, and that already tells you there can't be a tachyon. So what we have here are a whole bunch of states which are, from the space-time point of view, are scalars. and labeled with two indices. But these lambdas are anti-commuting oscillators, so this has AB anti-symmetry. And the indices A and B take 32 values. So we're dealing with this an anti-symmetric representation of SO32, which has 32 times 31 divided by 2, which is 496 different possible pairings. And this is precisely the adjoint representation of SO32. So what we have then in the ground state sector of the left movers is the scalars in the adjoint representation of SO32. But as before, these have to be tensored with the ground state of the right movers, which were this massless super Maxwell multiplet. And when you do this tensoring of this structure with this structure, lo and behold, you get exactly the field content of super Yang-Mills theory in 10 dimensions for gauge group SO32, because only the adjoint representation is appearing. Well, this is the complete description of the massless sector for the SO32 heterotic string theory. So there are two heterotic string theories in 10 dimensions associated with the two different gauge groups that are allowed by anomaly considerations. And this is a description of the SO32. So the question then arises, how would one have to modify this description if one wanted to understand the E8 times E8 heterotic string? But maybe before I do that, I can ask if any questions. This is very fast. And I'm skipping a lot of details that I assumed you're familiar with. No? Is there no? Okay. So let's move on to the E8 times E8 case. Well, we've clearly got to do something different. And one clue is the fact that E8, which I remind you is an exceptional Lie group. So let me take 1 minute to tell you what E8 is. So in the classification of compact simple Lie groups, there are 5 exceptional groups. This is the largest of the 5 exceptional groups discovered by Cartan. In this particular group, the index tells you the rank of the group. So this is a rank 8 Lie group, and it has 248 generators. 248 generators. And in particular, it contains a maximal subgroup, which is, say, SO16. So this is a subgroup. SO16 has 16 times 15 over 2 is 120 generators. And this is also rank 8, so there's no rank reduction in this embedding. And in fact, you can ask how the 248 of E8 decomposes with respect to this subgroup. And so it gives you 120, and that leaves 128 left over. And well, SO16 doesn't have spinners, but spin 16, which is the covering group of SO16, which is really what I'm talking about, but we don't always distinguish, has spinner representations, and a spinner of spin 16 has a dimension 128. There are actually 2 inequivalent spinners, so you could call them 128 and 128 prime. And depending on how you do the embedding, this is one or the other, and it's equivalent, so you don't really have to distinguish because there's an outer automorphism that interchanges them. So this is a useful fact to know this much, and it's sort of a key to understanding how this construction should work. Because if you know that E8 times E8 is what you want to find, then this says that in considering these lambdas, you should divide them into 2 sets. One set is lambda A, where A goes from 1 to 16, and the other is, I don't know, some other symbol, lambda prime A, or it's the same lambda, so I don't need a prime, where A goes from 17 to 32. So we just arbitrarily divide them into 2 sets of spinners, and we're going to have to somehow treat the 2 sets a little differently, because one of them is going to give rise to the SO16. You see, we want 2 copies of E8, so therefore we want 2 copies of SO16. So one of them will give one SO16, the other set will give the other SO16, and then we have to hope that some magic occurs, which provides the missing spinor representation of SO16 to complete the E8 adjoint representation. So that's basically the idea. And all this works, of course, otherwise I wouldn't be telling you about it. And so, oops, I got that a little bit too high there. Well, let's use the board over here. Here's the board. Okay. So, one can do this systematically and agnostically. You don't have to know that that's what you're headed for. You could just examine all possibilities, and you would, after a long analysis, you would discover that the possibility that I'm going to describe is the only other consistent possibility, at least for a supersymmetric theory. But to shortcut the discussion, I won't present it in that generality and just tell you the answer. So it's pretty clear that the massless spectrum that we want will still contain these states. That'll give us the supergravity multiplet for these states in the left-moving sector. But then we need to this massless part of the left-moving sector has to be changed somehow, because this is what gave us the adjoint of SO32. So it's clear that to get the adjoint of SO16 times SO16, we need this structure where A and B go from 1 to 16, and the same thing where A and B go from 17 to 32, because these states will give us the adjoint of SO16 times SO16 for the super Yang-Mills multiplet when tensored with the super Maxwell fields from the right movers. What we don't want are the cross terms where we have one lambda with an A from this set and another lambda with an A from that set. Because if we had those, then we'd be back to E8 times E8. So we need some rules that prevent that. And this has to do with the GSO projection rules that one chooses to do. So what one has here in this structure is an even number of oscillator excitations, and the fact that one is keeping an even number of fermionic oscillator excitations is part of the story about the GSO projection. And here the GSO projection rule was that we could have an even number of oscillators from anyone chosen from any elements of the set. So clearly here we need a different rule for the GSO projection, namely that there have to be an even number of these fermionic oscillator excitations when we restrict the indices to this subset or when we restrict to this subset separately. So it has to be even with respect to both subsets and not just combined. So it's a more refined GSO projection condition that separates the two subsets of the indices. So the case where you have one index belonging from 1 to 16 and the other from 17 to 32 is ruled out because that's odd with respect to either subset, and you have a rule that says that those are states that need to be projected out as this GSO projection condition. So the claim will be that that's a consistent rule, and then the question that remains then will be where do the spinor states come from? Well, the story is the same as for the superstring in the RNS formalism, and where do space-time spinors come from there? They come from the zero modes of these fermionic worldsheet fields, and so the story here is the same. So that means we have to consider the R sector. So the R sector means that for these left-moving oscillators here, so remember the periodic sector. So the periodic sector, remember, had integer modes, and the anti-periodic sector had half-integer modes. So far, I've only utilized the half-integer modes in my discussion so far. But to understand the spinor piece of the E8, one has to use the periodic sector with the integer modes. And when you have periodic boundary conditions, then these things have integer Fourier modes. And there's some obvious anti-commutation relations that look the usual story, that look like this. So you have anti-commutation relations, and when you quantize the worldsheet action, they'll look like that. And in particular, when you have zero modes, you have lambda 0 with lambda 0 gives you unit matrix. And those are exactly the anti-commutation relations of a Clifford algebra or Dirac algebra. And the representation theory, of course, of a Clifford algebra is that you represent it by spinors. And so the lambda zeros are analogous to Dirac matrices, same kind of algebra, and they act on spinors. Same story as for the superstring in the RNS formalism. And so the lambda 0a's acting on some spinor representation of the SO16 is then some kind of a Dirac matrix. Acts like some kind of Dirac matrix, where this is some kind of Dirac matrix. Now there are these 0-point energies that came up in these L0s. And because we're treating the two sets of 16 separately, we should really be talking about two separate 16-dimensional Clifford algebras rather than one 32-dimensional Clifford algebra. In the SO32 theory, where we had one 32-dimensional Clifford algebra, the normal ordering constant was such that this periodic sector would only contribute to the masses states in the spectrum. And since I'm focusing my attention in this discussion on the massless states, that is the reason we didn't discuss them previously. But now in this E8 times E8 case, where we have to look at 16-dimensional Clifford algebras, namely the indices A and B taking 16 values, with the normal ordering constants are such that you just have L0 on your state, physical state, has to have eigenvalue 0. So that means we don't want any oscillator excitations, but we need a representation of the lambda zeros. And these representations are exactly spinors of the spin 16. And so this periodic sector gives us the 128ths, both for the set A goes from 1 to 16, and second for the set A goes from 17 to 32. And that completes the E8 multiplet. And then one has the right, in terms of SO16, one has the right field content, and then one has to check that the theory really has the full E8 symmetry, which is a little additional work, which I will skip. Why is it 0? So for seeing what the eigenvalue L0 is, there are certain normal ordering constants that arise that can be understood from various viewpoints, but the issues that concern the determination of these normal ordering constants are whether you have periodic or anti-periodic boundary conditions, whether you're dealing with fermionic oscillators or bosonic oscillators, and how many of these oscillators there are. And when you have, so from the bosonic oscillators, one has basically a minus a half, just like one would have in the NS formalism for the right movers that come from the 10 x's. And so this gets an addition of a factor of a half. So for each set of these A's, if there are capital N of these A's, you get that number divided by 32 minus a half, and so you get 16 32nds minus a half gives 0. But in the case with the E8, with the SO32, the appropriate formula would have a 32 here, and then this would be positive. So So that's sort of a sketchy answer. There are various more precise ways of describing this, but I'd be happy to discuss further privately. So anyway, this is one of the two formulations of the heterotic string. And the other one is where you just use bosonic oscillators for the right movers and no fermions at all. So that was the case where the bosonic formulation is where we have these XLIs, where I goes from 1 to 16. And again, I can only summarize results. I don't have time to derive them. So the idea is as follows. First of all, that these x's should describe some 16-dimensional torus. And what the torus is a little awkward to write in terms of the x's, but one can do something equivalent and look at the Fourier transform problem, and the torus can be described by the spectrum of momentum excitations. So you have, given a torus, you have Kaluza-Klein excitations on the torus, and that gives you an infinite lattice of vectors. So in other words, a 16-dimensional momentum vector associated with an excitation of such torus will be given by integer combinations. So ni's are integers. And then you have basis vectors for a lattice, ei, I. So these are 16 basis vectors for a 16-dimensional lattice. And then, so arbitrary linear integer combinations of these 16 basis vectors give you an arbitrary momentum vector in this lattice. And knowing this lattice, lambda, which is encoded in the choice of these 16 basis vectors, is equivalent to knowing this torus. But the lattice is really the more convenient thing to talk about. Okay, I don't want this board to disappear just yet, so I'll move over here. So the quantity that appears is some function of a parameter tau, which is given by e to the I tau p squared, where the p is summed over the lattice. So you take all the vectors in this lattice. In other words, you sum over all these integers n, each of these integers n. All 16 integers are each summed from minus infinity to plus infinity. That describes the lattice. You're doing that sum in forming this object f of tau. Now, so describing this lattice tells you how you compactify these 16 dimensions. And then there's a consistency condition for one-loop amplitudes. So this sounds very fancy because I haven't even talked about tree amplitudes. But at one-loop amplitudes, there's a consistency condition known as modular invariance. And this modular invariance condition has to do with how this function transforms when we do an SL2Z transformation. Tau goes to C tau plus D. So ABCD is a matrix belonging to SL2Z. In other words, A, B, C, D are integers, and the determinant is 1. AD minus BC is 1. So that's the famous modular group. It's a group that shows up all over the place. It's associated with analysis of one-loop amplitudes. The reason being that a one-loop amplitude has a world sheet that's a torus, and this parameter tau characterizes the conformal structure or the complex structure of the torus. And the specific rule that's required for one-loop amplitudes in the heterotic string to have this modular invariance condition is that this f of tau should transform as a modular form of weight 8, which means that f under such a transformation goes to c tau plus d raised to the 8th power times itself. So that means it transforms as a modular form of weight 8. And if that is true, then the amplitude is modular invariant. And this modular invariance condition turns out to be equivalent, maybe stronger, but at least implies the anomaly cancellation condition. Because the anomalies that were present, except for the gauge groups SO32 or E8 times E8, are discovered at one loop. And so this modular condition ensures that everything is well behaved at one loop. And so if you're going to find any answers at all, it's got to have to do with these two groups, SO32 and E8 times E8, because we know from other considerations that those are the only ones allowed by this anomaly analysis. So this looks a little bit like esoteric mathematics, but it turns out that this requirement is precisely that the statement that this lattice lambda has certain properties, namely that it's what's called an even lattice and a self-dual lattice. So an even lattice is one for which the p squared, so p squared is even. So p squared is twice an integer for all lattice vectors. So that's an even lattice. And the self-dual is that if you form the dual lattice in the usual way, so in other words, you find basis vectors E star I such that E star I dot Ej is delta Ij. That defines the dual, so the dual lattice is generated by these vectors E star I. That's the dual lattice. And the E stars are not necessarily equal to E, but what is required is that they generate the same lattice. And so the self-duality is that the dual lattice lambda star is equal to the lattice lambda. So these two conditions turn out to be necessary and sufficient to ensure this property and the modular invariance. So that raises the mathematical question, what are the even self-dual lattices in 16 dimensions? And fortunately, mathematicians had already solved this problem before physicists asked it. In fact, about a year or two before this work on anomalies and the heterotic string, there was a very nice review paper by Peter Goddard and David Olive, which described this stuff in great detail. Peter is now the director of the IAS, and that work was very helpful in guiding this program. So the classification, so I'll just talk about Euclidean. So these are, Euclidean just means that the metric for this lattice is positive definite. So for Euclidean even self-dual lattices, there are a couple of basic facts. So the fact number one is that they only exist if the dimension of the lattice is 8 times an integer. For any other dimension, they don't exist. So the first example, therefore, is in dimension 8. First example of an even self-dual lattice. And it is the lattice generated by the roots of the Lie group E8. So it's the E8 root lattice is the unique example in 8 dimensions. Well, we don't really need that fact directly because we're interested in 16 dimensions, but it's a useful fact anyway. But that fact already tells us one answer. for 16 dimensions, because if you have an even self-dual lattice in 8 dimensions, it's very easy to make a corresponding one. So if I call this lattice lambda 8, then I can immediately make a 16-dimensional even self-dual lattice is just the direct sum of two such lattices. So that's one example of an even self-dual lattice in 16 dimensions. And the choice of this lattice, I think you will believe me, leads to the E8 times E8 heterotic string. And the second alternative that exists in 16 dimensions is a lattice we could call lambda 16. And it's associated to the weight lattice of spin 16. Well, spin 16, if you look at the weights of spin 16, they fall into 4 conjugacy classes. There's the weights associated with the adjoint representation. They generate what's called the root lattice. Then there's another lattice that's shifted from the root lattice by a vector weight, and by say a 16-dimensional representation. It's a vector representation. So the weights of this Lie group associated with the vector representation give you a shift in the root lattice. And then there are 2 other shifts that you can define, which give you 2 more lattices, which are shifted by spinorial weights. We have these 228-dimensional spinor representations, and each of them has weights associated with them that give you other shifts to the root lattice. So we have these 4 different lattices that can be combined in various ways. If you took all 4 of them, that would be the weight lattice of spin 16, and that's not what we want. What we need is that this should be the sum of 2 of the 4. So the way people usually write it is they say it's the weight lattice of spin 32 mod Z2. That's a fancy way of me saying that they're going to use 2 of the 4 conjugacy classes. So you use the root lattice, and then one of the shifts of the root lattice by a spinorial weight. So that gives you 2 of the 4 conjugacy classes, and those 2 combined can be viewed as the weight lattice of this group, and that is the lattice that's even in self-dual. And so, in fact, that tells you that in the physical spectrum of the SO32 heterotic string, the representations of the group that appear will belong to these 2, to this group, if you want to be very precise. So there will be spinor representations in the spectrum, but only 1/2 of the type of spinor representations will appear and not the other half. Okay. I've already used more than half of my time, and I'm still in chapter 7. And I was going to describe toroidal compactification of the heterotic string. Do you want me to do that, or should I move on to chapter 8?
Move on to chapter 8, and maybe this afternoon say a bit about the toroidal.
Okay. Okay. Any questions? So, now for something completely different, as they say. So in the mid-90s, there was a lot of development in string theory, sometimes referred to as the second superstring revolution. And the developments had to do with understanding non-perturbative aspects of string theory. And everything that I've discussed yesterday and so far today are things that can be understood within a perturbative framework. And it was clear to everybody in the business for a long time that we needed more, but it took a while to figure out how to get our hands on it. And so the things that are developed are something called Mtheory, and also what I could call non-perturbative dualities. So I want to say a little bit about these things. Now, we don't have a complete understanding today of non-perturbative string theory, but we learned quite a bit, and we've learned more since then, which is described, for example, in Chapter 12, which we won't talk about. In any case, this represented significant progress, even if it's not the complete final story. So what is M-theory? Well, in 1978, Kremer, Julia, and Shirk formulated a supergravity theory called 11-dimensional supergravity. This is a very beautiful, mathematically beautiful classical field theory that includes gravity, and it's very special because one can show just from the representation theory of supersymmetry that this is the highest dimension in which it's possible to have an interacting supersymmetrical theory. So this is a very special theory, and everything we knew for a long time about string theory said that 10 is the right dimension to be talking about, not 11. And I can remember even in 1984 being at a meeting where Mike Duff was one of the speakers, and I was another, and I kept insisting that he was making a 10% mistake by talking about this. But it was clear that it was a beautiful theory and ought to fit into the story somewhere. And it took a long time to figure out where. One thing we knew way back, even in those days, that if we did what's called a dimensional reduction. So what is a dimensional reduction? Well, you imagine taking one of the 11 dimensions to be a circle, and then you assume all the fields are just constants on that circle. You only keep the 0 Fourier modes on that circle. Then you get rid of that circle and you just reinterpret what you have as a 10-dimensional theory. So if you do that, so you do a dimensional reduction to 10 dimensions, so just drop the dependence on one of the coordinates, that gives you a 10-dimensional supergravity theory. And that 10-dimensional supergravity theory precisely describes the massless sector of type 2A superstring theory. So it's the type 2A supergravity. So that we knew before this revolution, or even before 1984 for that matter. Okay, so that was a hint, but we didn't know how to exploit that hint. So before I tell you how to exploit that hint, let me just tell you a little bit about 11-dimensional supergravity. Well, one reason that I insisted that it was a 10% error was because in the case of the 10-dimensional theory, we knew how to interpret it as a quantum theory, at least within a perturbative framework by using string theory. But in the case of 11-dimensional supergravity, there are no strings. There is no analogous perturbation expansion, and so the claim was that this is simply a non-renormalizable theory, and because it's in 11 dimensions, it's much worse than any theory like that in a lower dimension. So it was horrendously non-renormalizable. So that was the objection. Another physical objection is that in any odd dimension, you always have parity conservation. It's left-right symmetrical, and therefore this couldn't have anything possibly to do with the standard model. Couldn't be relevant to real-world physics, because where was parity violation going to come from? So those are the main objections to talking about 11-dimensional supergravity in those days. All these issues, of course, have answers now, but they didn't then. So what I want to tell you about 11-dimensional supergravity is the field content. So you have the graviton in 11 dimensions. So massless fields in d dimensions are classified by representations of the little group, which is spin of d minus 2. So in this case, spin of 9. And this is a symmetric traceless representation of spin 9, which has a 44. It's a 44-dimensional representation. So a graviton in 11 dimensions has 44 different polarizations. The second field is the gauge field for local supersymmetry. So it's a Rorita-Schwinger field that makes local supersymmetry. And the appropriate representation of spin 9 is a vector spinor thing, and it turns out to have dimension 128. It's given by a Majorana spinor and various gauge invariances and so on and so forth. So to have an equal number of bosons and fermions, we need 84 more bosons. And the thing that works is a three-form field, A mu nu rho, or just A3 in my notation from last time. So it's a three-form field. And this three-form field defines a representation of spin 9 of dimension 9 times 8 times 7 divided by 1 times 2 times 3. And that's 84. So with these three fields, one has 128 bosons and 128 fermions. And Crémer-Julian-Shirk wrote down a beautiful formula that describes a Lagrangian with local supersymmetry based on those three fields. So that's 11-dimensional supergravity. One more fact about this theory, or about any such theory, is that since it has local supersymmetry, you can say how each of these fields transforms under a local supersymmetry transformation. So delta G and delta A3 do whatever they do. Actually, one can't use the metric tensor because you have spinors. You have to use an Elfbein. So you have to use a so-called frame or bind formalism to formulate the theory. But I'll ignore that fact here and just write delta G. So the delta G and there's a delta A3 are given by some formulas, which I don't need. And delta psi is also given by some formula, which is a little bit complicated. It not only involves some covariant derivative of the parameter of the local supersymmetry, but it involves various terms that involve the field strength based on A3. So out of A3, you make a field strength F4. F4 is dA3. And then this thing gets contracted with Dirac matrices in various ways, so it's a little bit complicated, and then that multiplies epsilon. So there are formulas like this for the local supersymmetry transformations. And the reason it's useful to be aware of this is because one of the things one would like to know is how does one find solutions of this theory? In other words, solutions of the classical equations. And we're interested in particular in solutions of the classical equations that preserve some of the supersymmetry. Preserving some of the supersymmetry means that there are non-zero epsilons for which expressions like this vanish on a specific solution. So setting this equal to 0 for given F4 and given geometry can be viewed as an equation for epsilon. And that equation is called the killing spinor equation. One could also talk about these equations, but the right-hand sides vanish trivially because in a classical solution, the Fermi fields are equal to 0. And these expressions have Fermi fields on the right-hand side. So I don't need to study them to define the killing spinor conditions. These are, of course, analogs of the killing vector equation, which do the same thing for bosonic symmetries. So in a statement like that, something like this vanishes is the killing spinor equation, and that you can view that either as an equation for epsilon or as a condition on the geometry for the existence of epsilons. And there are certain examples of solutions that preserve all of the supersymmetry. Well, 11-dimensional Minkowski space does in a rather trivial way because everything's basically 0. So that's not too interesting. So anyway, 11-dimensional Minkowski space works. But what's more interesting is that two other examples that preserve all of the supersymmetry are a product of an anti-de Sitter space and a sphere of these particular dimensions, or of another anti-de Sitter space and another sphere of these dimensions. So these are two examples of geometries. And then in these geometries, there are non-zero fluxes, F4. So the way that works is that F4 integrated over the 4 sphere is some integer. Or in this case, the dual of F4 integrated over the sphere is some integer. So there's actually an integer that characterizes each of these solutions. And these are fully symmetrical solutions, which are of great interest in modern research. Enough said. So now the reason that one takes 11-dimensional supergravity seriously is because it's believed to be a low-energy approximation to a deeper theory, which is well defined as a non-perturbative quantum theory. And this deeper theory has been given a name even though it hasn't been formulated. And the name is M-theory. So M-theory is the quantum theory whose low-energy effective action is 11-dimensional supergravity. That's the definition. So now the claim is that even though we don't know M-theory, we do know that these particular solutions are exact solutions to M-theory. So it's kind of remarkable. Without knowing the theory, you can have an exact solution. And the reason is that there is an effective action where you supplement the 11-dimensional supergravity with the terms of higher and higher dimension that are mostly unknown. A few of them are known, but mostly unknown. And one can argue very generally that whatever those terms are, they all vanish on these particular solutions, so it doesn't matter what they are. So therefore, you have a solution because of all the supersymmetry, basically. Okay, so M-theory. So I mentioned that there should be a connection to type 2a supergravity. And, well, there is a connection to type 2a supergravity. So rather than just saying that dimensional reduction to 10 dimensions give type 2a supergravity, one can do better and ask what happens if we consider M-theory on 10-dimensional Minkowski space tensored with a circle. So in doing dimensional reduction, we just took the zero modes on the circle. And then they said that's if we just take 11-dimensional supergravity and take the zero modes on the circle, that's type 2a supergravity. But now if we take unknown M-theory and we don't throw away modes on the circle, the claim is that taking the whole theory, whatever it is, in this geometry, the claim is that this is precisely type 2a superstring theory. And furthermore, there's a relation between certain parameters. So there's the 11-dimensional type 2a superstring theory has a string coupling constant that's given by the vacuum expectation value of the dilettone field. Anyway, it's just a number. It's the parameter that you do expand in when you do perturbation theory. And there is no analogous parameter in 11 dimensions in R10-1. And then if you multiply that by the fundamental string scale, this is supposed to equal the radius of this circular 11th dimension. So that tells you one of the relations. There's another formula we can write down in a moment. I can write it down right away, I guess, if I have it. Well, we'll derive it. Well, if this is true, we have to understand where the type 2a superstring comes from, because I told you there are no strings in 11 dimensions. And the clue to that is to remember something we discussed last time, and that is when we had these form fields, that there were associated branes that carry conserved charges. So when we have a 3 form in 11 dimensions, we can ask what kind of branes would this couple to that would have conserved charges. And such a form would couple electrically, namely this way, to a world sheet that has 3 dimensions, and that's what we call a 2-brane, right? Because we never count time, we just count the spatial directions. So there's a 2-brane that would couple electrically to this 3 form, and this 2-brane, since it belongs to M-theory, is called the M2-brane. And then there's a magnetic dual to the remember we always have this electric-magnetic pairing of these branes, and the magnetic dual, so that the brane that couples magnetically to this 3 form turns out to be an M5 brane. So there are these 2 types of stable objects in 11-dimensional supergravity, which you can think of as infinite hyperplanes if you want to make them really stable. The only other way to make them stable is to have compact dimensions and wrap things and so on. Okay, so each of these, there are solutions of 11-dimensional supergravity that correspond to these things, which are higher dimensional analogs of black hole solutions. And those solutions preserve half the supersymmetry of the full theory. So these, just like the D branes we discussed yesterday, these are 1/2 BPS, meaning the corresponding solutions preserve half of the supersymmetry. So these are fundamental objects in M theory, and they're basically the only ones. With minor, well, there are some other things too. Okay. So where is the type 2A superstring going to come from? Well, there's an obvious answer. These are the only objects we have in 11 dimensions. But if we have a circle like this, what we can do is to imagine that this M2 brane, say, has a toroidal geometry. And if it has a toroidal geometry, we can wrap one of its cycles on the cycle of the space-time. And then that will leave an object which, viewed from the other 10 dimensions, looks just like a loop. Right? Because we've got a circle times a circle. We've used up one of the circles on the internal dimension. If we now make this internal dimension so small you can't see it, then all you're left with is a loop. And that's the type 2A superstring. So the M2 brane wrapped on the S1 is the type 2A string. This assertion is supplemented by formulas. So for example, this M2 brane has a certain tension. Let me call it Tm2. And if we take that tension and multiply it by the circumference of the circle, so remember this is to be viewed as an energy density. So if we multiply this by 2 pi r, or R11 I called it, this has got to give you the tension of the type 2A string. So one has a formula like that, which allows you to relate parameters of the M theory to parameters of the 2A string. And that formula plus another formula allows you to deduce this formula, which I haven't explained yet. Well, what's another formula that needs to be explained? Well, the type 2A string, the type 2A string theory, has other stable objects besides the fundamental string. Namely, it has D branes of even dimension. So remember, the stable objects in type 2A were the D0, the D2, the D4, etc. So where do they come from? Well, the D0 is an interesting case. And the way so it's a point particle excitation. So where are we going to get, it's massive and supersymmetrical. Where are we going to get such an object out of this construction? Well, 11-dimensional supergravity just had massless fields, and it has a circle. So what you can do with massless fields in a circle is you can look at the Kaluza-Klein spectrum on the circle. And that gives you states whose mass is n over r, where n is an integer. So R11, I called it. So these would be the masses of the Kaluza-Klein excitations of these massless 11-dimensional particles. These would be the 10-dimensional masses that you would get from the Kaluza-Klein excitations on the circle. And the claim is that the first excitation, which is the one with minimal non-trivial mass, is a stable particle from the 10-dimensional viewpoint, and it is the D0 brane. And the D0 brane happens to have a tension 2 pi G string L string. And, this is let's see, so what did I do wrong? 2 pi. Oh, there is no 2 pi, that's what I did wrong. This is the mass, this is the tension of the D0 brane that's known from other considerations, such as supersymmetry, in the 10-dimensional type 2A theory. And you see that the formula I wrote earlier is just this equation in disguise. So this is actually a hidden way of saying that the D0 brane is the first Kaluza-Klein excitation on the circle. You may ask, what is the second Kaluza-Klein excitation? Well, it's a bound state of 2 D0 branes, etc. Okay. You can ask about some of the other branes, such as the D2 brane. Well, the D2 brane is easy. It is an M2 brane. But not just any old M2 brane. It's one that's not wrapped on the circle. If you go to the covering space of this, in other words, you place the circle by a line, you can describe equivalent physics by requiring periodicity on that line. So in terms of the covering space, the D2 brane is a periodic array of M2 branes. But it's really a single M2 brane when you quotient out by this period to form the circle. But mathematically, the precise relation would involve that periodic array. So the M2 brane is the D2 brane. And it has a known tension, which is 1 over 2 pi squared G string L string cubed. So, and then again, this can be written in terms of the parameters of 11-dimensional supergravity. And doing that, one gets this relation plus one more relation. And the remaining relation relates the 11-dimensional Planck scale to the string scale. And if I'm doing this from memory and I may have it wrong, but as I remember, the coefficient is G string to the 1/3. So these two relations are relate the two parameters of type 2A, which is the string coupling and the string length scale, to the two parameters of M-theory, which are the 11-dimensional Planck length and the radius of the circle. The D4 brane, well, that's easy. You take the M5 brane and you wrap it on the circle, and that gives you the D4 brane. The D6 brane, that's more challenging. It's a Taub-Nut solution to the M-theory. So it's the analog of a Kaluza-Klein monopole for this circle. I won't explain that further. Okay. So that's that part of the story. So in this way, one has learned something about the non-perturbative physics of type 2A superstring. Namely, at strong coupling, the type 2A string becomes 11-dimensional. See, when we were doing perturbative type 2A string theory, we were expanding about G string equals 0, but G string equals 0 means the radius of the 11th dimension is 0. So in perturbation theory, the 11th dimension was completely invisible. So that's why we didn't know about it for so many years. So you have to go beyond perturbation theory and understanding to realize that there is an 11th dimension, and then you understand that at strong coupling, the type 2A string theory is M theory with a circle, and the circle becomes infinitely large if you go to the strong coupling limit. And you recover full 11-dimensional Lorentz invariance. The graviton is a mode of the superstring.
Yeah, it's a mode of the superstring. We cannot view the graviton and M-theory as a mode of.
Well, see, what some people have tried to do is to take the M2 brane and analyze its excitation spectrum the way you do with a superstring. But that doesn't really work. You can't do that. The only stable point-like objects in 11 dimensions uncompactified are just the massless fields of the supergravity theory. There is no additional spectrum of excitations. The reason the 10-dimensional string theory has an infinite spectrum of excitations on top of the massless ones is because we have this parameter G string, which can be made very small. And all these massive excitations become stable as G string goes to 0. When G string is large, they completely dissolve into mishmash, and they're nothing. And in the strong coupling limit, where you get to 11-dimensional supergravity, the only thing that's even approximately stable are the massless modes.
And they're not excitations of anything.
I'm sorry?
They're not excitations of any object.
So, well, as I said, we don't really have a fundamental formulation of M theory. So that's why it's a little awkward to give you a good answer to that. But what we do have is this low energy effective theory, 11-dimensional supergravity, which is based on the massless fields.
And a related question is, when you say D0 is the multiplying excitations of the S1,
Yes.
what is carrying that momentum?
What's carrying what?
The momentum.
Oh, that's the usual story and includes decline. What you do is you consider a wave function on the circle, and you require that x is periodic, because it's parametrizing a circle. And then you want this to be single valued. And so therefore, the momentum along the circle has to be a multiple of 1 over r in order that this be single valued.
I guess I was asking, say it could be a photon or something which is carrying the momentum. What is the object?
Oh, it's the entire supergravity multiplet of the 11-dimensional theory. So each of these D0 branes is a supersymmetry multiplet. It's not a unique state. It has 256 polarizations, 128 bosons, and 128 fermions. So it's just an exit. It's the whole supergravity multiplet lifted. You see, when we had the little group spin 9 in 11 dimensions, which classified these things. This is the classifying group for massless particles in 11 dimensions, but it's also the classifying group for massive particles in 10 dimensions. Because the general rule is that for massless particles are classified by a little group spin of d minus 2, and massive particles are classified by spin d minus 1. So whatever was massless in the higher dimension can be massive after the compactification. And it's the same representation theory. Please.
Yeah, I'm confused by related to the last question. When you take the M2 brane and wrap it around the circle,
Yes.
you get the type 2A string.
Yes.
And the type 2A string has massless graviton modes.
Yes.
But you also have massless graviton modes coming out of the 11-dimensional supergravity.
Yes.
So are you double counting massless gravitons?
Well, no, but I can understand your concern. So there are two things you could do in the type 2A theory. One is to discover the spectrum by quantizing the string, or the other thing you could do is just examine the low energy effective supergravity theory. And the gravitons you're describing by either procedure are the same gravitons. And those correspond to the two options that you listed. Any other questions?
Maybe comment at least that the fact that the n over r11 is indeed the mass of the n, the 0 branes combined, had to indeed be sort of verified.
Yes.
As indeed one of the proofs, at least one of the evidence.
Right. Right. Yeah. So what Herman said, and is right, of course, is that for this interpretation that I proposed in terms of D0 branes to make sense, it was necessary that there should exist a bound state of ND0 branes with zero binding energy. It's what's called a threshold bound state. And it's a highly non-trivial question when threshold bound states exist and when they don't. And it requires a very sophisticated mathematical analysis to verify from other viewpoints that that bound state really does exist. And that has been checked. Okay. What? Yes.
But by duality, we can obviously see that two D0 branes are like momentum. But if you have two momentum in a certain compact direction,
Yes.
then the bound state should be found threshold bound state. Why is it?
Yes, that's right. Threshold bound state. The point is that the n d0 brane bound state has n times the mass of the single d0 brane, so there's no binding energy.
But by duality, it's like two momentum modes getting bound together in some sense.
Yeah, right.
Not obvious.
Well, I mean, you can have separated d0 branes also. They exist as well as multi-particle states, but the existence of the bound states is required. Okay, so let's move on in my remaining 5 minutes to talk about S-duality. So this was something that was understood first in the type 2b superstring theory. The type 2a superstring theory contains two scalar fields. One is the dilaton phi, whose expectation value determines the string coupling constant, as I've mentioned a couple of times. And another scalar field in the type 2b theory is the Ramond zero form, which is the thing to remember that's related to the d instanton. And it turns out that the supergravity theory has a symmetry SL2R. And the way to describe this symmetry is to introduce a parameter tau, which is C0 plus I over G string, basically. Or, I'm sorry, I don't want that. I want I e to the phi. I want the field. So the e to the minus phi. So the expectation value would give you 1 over G string here. So this is a complex scalar field that encodes these two real scalar fields. And now the claim that this theory has SL2R symmetry has to do with invariance under transformations of this complex scalar field of this form, where A, B, C, D belong to form a matrix SL2R. That's for the type 2b supergravity. But when you go to the string theory actually breaks this group down to the discrete subgroup SL2Z. And when you have SL2Z, then A, B, C, D have to be integers. There are other fields that transform in a non-trivial way in this theory. So there are two forms. There's a B2, which is the NS-NS2 form that exists in the spectrum. That's the field that couples to the fundamental string. And then there was the Ramond 2 form that is the thing that couples to the D string. And these two fields transform as a doublet under this transformation. Well, I may need the transpose or the inverse or something of this matrix, but it looks roughly like that. The other fields are basically singlets. Now, this SL2Z is important for the following obvious reason. One of the transformations that generates SL2Z is the transformation in which tau goes to minus 1 over tau. That corresponds to a matrix that looks something like that. Now, suppose we'd look at a particular geometry in which C0 is 0. And then inverting tau just means changing, tau goes to minus 1 over tau, is just taking e to the minus phi to e to the phi. So this transformation when C0 is 0 just sends phi to minus phi. But in terms of the vacuum expectation value, that's sending the string coupling constant to its reciprocal. So here is a symmetry, an alleged exact symmetry of type 2b superstring theory, in which the string coupling constant transforms to its inverse. That's profound, because prior to this, we only understood perturbation theory was an expansion about G string equals 0. So now the claim is that the expansion about G string equal infinity is exactly the same as the expansion about G string equals 0. Of course, you still don't understand this theory when G string is equal to 1. But nonetheless, it's progress. Okay, so in my remaining 1 minute, let me tell you how to understand this symmetry from the point of view of M theory. So, what we will do is we'll take the type 2B theory, which is a 10-dimensional theory, and we will compactify it on a circle to get some 9-dimensional theory. Now we know that type 2B on a circle is related by T-duality to type 2A on a circle. And I've told you that type 2A can be understood as M theory on a circle. So putting those two facts together, we can start with 11-dimensional M theory and compactify on a 2-dimensional torus and get to the same 9-dimensional theory. Now, when we have a compactification on a torus, this torus is described by a modular parameter tau. And the torus, if you replace tau by a tau plus b over c tau plus d, by one of these modular transformations associated with SL2z, that's the same torus, an equivalent torus. So M theory on a T2 has what you might call a geometric duality, a relatively trivial duality, which is this SL2z, which is just the modular group of the torus. But from the point of view of this 9-dimensional theory, that turns out to be the same SL2z as the non-perturbative symmetry of the type 2B theory. So you deduce in this way that this 9-dimensional theory has an SL2z symmetry. And now, holding tau fixed, you can squeeze this torus to 0 size, send its volume to 0, and that's related by a duality to sending this circle to infinity, because you remember T-duality has the circles going the opposite ways. So when you shrink this torus to a 0, you're blowing up this circle, you get back to 10-dimensional type 2B string theory, and you see that, and this symmetry remains back in 10 dimensions. So there's this very nice coherent picture, and this is a tip of an iceberg, but my time has run out, so the rest of the iceberg you'll have to find by reading.